Hello everyone. Today we'll discuss about numerical differentiation. Before we'll start discussing numerical differentiation, let's discuss first what is calculus. Calculus is a branch of mathematics that involves the study of rates of change. Most of the equations in physics use calculus. There are two types of calculus. We have differential calculus, which determines the rate of change of a quantity, and integral calculus finds the quantity where the rate of change is known. What is differential calculus? The derivative of f of x at point x equals a is the slope of the tangent to f of a. So we have here a function x sine x squared plus 1. So this is the curve of the function, and the derivative at point A is equal to the tangent line of that point. Okay, so you can observe in this animation at this point we have here a tangent line. So this tangent line indicates the derivative of the function at that point. Now we know that the slope is just delta y divided by delta x, and we can expand this delta y from f of x plus delta x minus f of x, meaning the next value of our function minus the present value of our function divided by the delta x, or the change in value of our x. Since we are deriving at point A, so we need to make this delta x closer to 0. So the formula becomes slope equals limit of f of x plus delta x minus f of x divided by delta x as delta x approaches to 0. Now let's go to our main topic, which is numerical differentiation. So what is numerical differentiation? Numerical differentiation is the process of finding the numerical value of a derivative of a given function at a given point. So we'll be using computer to find the numerical value of a derivative. So first, you'll find f prime of xi, or the derivative of f of x, is equal to our function of xi plus 1, which is the next value of our function of f of x minus f of x divided by xi plus 1 minus xi. So this is the next value minus the current value plus some error, where the error is a function of xi plus 1 minus xi. So we can change this formula to delta f of I and delta f of I divided by h. So where h is equal to xi plus 1 minus xi. So delta fi is referred to as the first forward difference, and h is called the step size. If we have forward difference, we have also backward difference. The backward difference f prime xi is equal to the present value of our function f of xi minus the previous value f xi minus 1 divided by xi minus 1 minus xi. So we can change this formula to nabla fi over h plus some error. So the error is O of h, and nabla fi is referred as the first backward difference. So this is the graphical representation. first we have forward difference. So if this is our current value, then this is the next value. So this is the forward difference, and this is the true value. This is the slope of the true value, and this is the slope of our approximation. As you can see, it is not close to the true value. So this slope is not close, similar to this true derivative. And for our backward difference, this is the previous value and this is our current value. So this is the slope, the approximation of our slope, but this is our true derivative. As you can see, our approximation is very far from the true value of our derivative. So the solution for that is we'll be using centered finite divided difference approximation. So what we'll be using is the next value minus the previous value and divided by 2h, since our step size was doubled. So as you can see, our approximation value is closer to our true value. So central difference is f prime of our xi equals the next value of our function minus the previous value of our function divided by 2 times xi plus 1 minus xi minus 1 minus our error, and our error is function of h squared. So as you can see, the error in our central difference is smaller compared to the forward and backward difference. So we have here an example. So we'll be using forward and backward difference approximation of OH and a center difference approximation of OH squared to estimate the first derivative of f of x equals negative 0.1 x to the fourth minus 0.15 x cubed minus 0.5 x squared minus 0.25 x plus 1.25 at x is equal to 0.5, using the step size h equals 0.5, and we'll repeat the computation using h equals 0.25. And note that the derivative can be calculated directly as f prime of x, which is equal to negative 0.4 x cubed minus 0.45 x squared minus 0.1 x minus 0.25. So if we substitute the value of 0.5 in our derivative, then we will get a value of negative 0.9125. So to find the solution, first we need to find the value of our xi. Okay, so our xi minus 1, so this is our previous value, is equal to 0, and our present value xi is equal to 0.5. So basically, since our h is 0.5, then our current value is 0.5 minus 0.5, then that is our previous value, 0. Now our next value xi plus 1 is equal to 1. So we just add 0.5 with our h, our step size. So this is now our xi minus 1, xi, and xi plus 1. So now let's substitute the our value of xi minus 1 to our function. Using calculator, we'll get 1.25. Okay, so basically the value of our x is equal to 0, then this will be 0, this will be 0, so we're left with 1.25. So this is our f of xi minus 1, or f of 0 is equal to 1.25. So next, our f of xi, which is equal to 0.5, so we'll replace x to the fourth with 0.5 to the fourth, and x cubed by 0.5 0.5 cubed, and 0.5 squared, and 0.5. Okay, so using calculator we'll get a value of 0.925. Okay, and last is our f of xi plus 1. So we'll replace x with 1. So using again our calculator, we'll get 0.25. Okay, so once we arrive with this value, then we can calculate the forward difference, the backward difference, and center difference. So for our forward difference, we have f prime of 0.5, which is equal to our next value, which is 0.25. Okay, so this is our next value, 0.25 minus our current value of 0.925 divided by our delta our h, which is equal to 0.5. So we'll get negative 1.45. So to calculate the true error, okay, so we have our absolute value of our negative 1.45 minus negative of our true value, which is equal to 0.9125. Okay, so divided by 0.9125, okay, times 100%. So our true value error is equal to 58.9%. Okay, so the error is very big. So now let's go to backward difference. So in backward difference, we have f prime of 0.5, which is equal to our present value, which is 0.925, minus the f of 0, which is 1.25, divided by our step size of 0.5. So this is equal to negative 0.65. Okay, so we'll get the error. So our true value error is equal to the absolute value of negative 0.65 minus the negative of 0.9125 divided by 0.9125 times 100%. So our error for this one is equal to 28.77%. Now let's go to central difference. So in our central difference, we have f prime of 0.5, which is equal to the next value, which is 0.25 minus the previous value of 1.25 divided by 2 times our h of 0.5, so which is equal to negative 1. So we'll find the true value error. So we have negative 1 minus negative of 0.9125 divided by 0.9125 times 100%. So our true value error is just equal to 9.6%, which is very low. Now, to save time, we'll use a Python code to solve for h is equal to 0.25 for forward, backward, and central difference. Okay, so first I assigned the true value of negative 0.9125. Then I define a function f of x, which is equal to this one, negative 0.1 times x to the 4 minus 0.15 times x to the 3 minus 0.5 times x to the x squared minus 0.25x plus 1.25. So I define a derivative function which will give the number the number of computed derivative at x equals a, and then the method, so whether it will be central, forward, or backward. So our default method is central. Okay, and our h is equal to 0.25 sorry, h is equal to 0.25, so which is our default value. So if the method is central, then we have f of a plus h, which is the next value, minus f of a minus h, which is our previous value, divided by 2 times h. Okay, so this is our formula. And for forward difference, so we have f of a plus h minus f of a divided by h. And for our backward difference, we have f of a minus of f of a minus h divided by h. So our f prime, so our result is equal to the derivative of 0.5. So our value of our x is equal to 0.5, and then the method I'll be using is forward, and our h is 0.25. Okay, so if we run this one, we'll get the value of negative 1.1548, which has an error of 26.54%. Okay, so we'll just change from forward to backward. So if we run this one, we have negative 0.714 with an error of 21.7%. Okay, and then we'll try central difference. Okay, so for central difference, our value is negative 0.9343 or negative 0.9344 with an error of 2.39%, so which is very low. So compared to forward and backward difference, so we have an error of just 2.4%. So I hope you learn a lot from solving differential equation to using Python code to find the value of our numerical differentiation. So see you guys, and Bye-bye.